Now we're going to talk about the differential. The differential will be used going forward in the class, but we still need to look back at the definition of the derivative. If you remember, when we compare the graph of a function and its tangent line at a point, we're looking at slopes, x or dx. That's our change in x, and that's going to give us a change, obviously, in the function values. So let's start off with some definitions. So dx is called the differential, which is the change in x between 2 points, either on the tangent line or on the function itself. Dx is equal to delta x. So then the dx is called the differential because it's just basically the change in x. So now we're going to look at the change in y, but we actually have two y values, right? We have, if we're looking at the tangent line and the function, one of our y values is actually on the function. One of our y values is actually on the tangent line, right? So for at x plus delta x, this red point is on the tangent line at x plus delta x, but this black point is on the graph at x plus delta x. And the tangent line is giving us an approximation to this one. So the actual change in y along the real function that we're given is delta y. So the change in y is just f of a plus delta x minus f of a. So dy is called a differential, and it's the change in y values between the points on the tangent line. So this red distance, vertical distance, up to the tangent line is dy. And that's just basically the change in the y value between 2 points on the tangent line. So dy is defined as L of a plus delta x minus L of a. So it's just that vertical change as you go from one point to the other on the tangent line. And it's this dy that we'll be using for approximations to our function. So right now dy is in terms of the tangent line. So let's get it in terms of the function now. So remember the definition as far as the linear equation for the tangent line. So if I replace L of a plus delta x with this equation, this simplifies. I'm replacing the x in L of x with a plus delta x here. And this simplifies to f prime of a times delta x, because these a's subtract out, plus f of a. So now I've gotten that, and now I'm going to subtract L of a. So I replace x in this equation with a. And when I do that, this gives me 0, so I'm just left with f of a. So then dy simplifies to f prime of a times delta x plus f of a minus f of a, or simply f prime of a times delta x. And remember, delta x is equal to dx. So remember, a is just some arbitrary value of x. So I can apply this to any value of x. So when my difference in x is not equal to 0, I can say f prime of x equals dy over dx. So we've seen this before, and we might be saying, well, big deal, we've known that the tangent, the slope of the tangent is just the derivative. And that's really all we're saying here again. The slope of the tangent line is dy over dx, which is just the derivative of the function.